Now that you've mastered the art of importing flat files in Python, it's time to check out a number of other file types that you will find yourself needing to work with as a data scientist. In this chapter, you'll learn how to import Excel spreadsheets, which professionals from all disciplines use to store their data. You'll also gain familiarity with importing MATLAB, SAS, and Stata files, all of which are commonplace. You'll also learn how to import HDF5 files, and you'll actually import an HDF5 file containing data from the Laser Interferometer Gravitational Wave Observatory project that provided empirical support for Einstein's theory of gravitational waves in 2016. HDF5 files are becoming a more prevalent way to store large datasets, as demonstrated by the fact that the LIGO researchers used it to store their data. Another file type you'll learn about in this chapter is that of a pickled file. This is a file type native to Python. The concept of pickling a file is motivated by the following. While it may be easy to save a NumPy array or a pandas data frame to a flat file, there are many other data types such as dictionaries and lists for which it isn't obvious how to store them. Pickle to the rescue! If you want your files to be human readable, you may want to save them as text files in a clever manner. JSONs, which you will see in a later chapter, are appropriate for Python dictionaries, for example. If, however, you merely want to be able to import them into Python, you can serialize them, aka pickling them. All this means is converting the object into a sequence of bytes or byte stream. As this is a course in importing data in Python, you'll learn how to import files that have already been pickled. As you've done before, when opening such a file, you'll want to specify that it's read-only. You'll also want to specify that it's a binary file, meaning that it's computer readable and not human readable. To specify both read-only and binary, you'll want to pass the string RB as the second argument of open. You'll then dive headfirst into Excel spreadsheets, the use of which is so widespread that they need next to no introduction at all. An Excel file generally consists of a number of sheets. There are many ways to import Excel files, and you'll use pandas to do so, because it produces data frames natively, which is great for your practice as a data scientist. As you can see in this example, you can use the function Excel file to assign an Excel file to a variable data. As an Excel file consists of sheets, the first thing to do is to figure out what the sheets are. Now this is straightforward with the command data.sheetNames. To then load a particular sheet as a data frame, you need only apply the method parse to the object data with a single argument, which is either the name as a string or the index as a float of the sheet you wish to load. Pandas is clever enough to know if you're telling it the sheet name or the index. You'll also learn how to customize your spreadsheet import in order to skip rows, how to import only certain columns, and how to change the column names. Now that's enough from me. It's now time to get your hands dirty with pickled files and Excel spreadsheets. Enjoy! There are many statistical software packages out there, and although you may not need to do so all the time, it will be important for you, as a working data scientist, to be able to import these files into your Python environment. The most common examples are SAS, which is an acronym for Statistical Analysis System, and Stata, which is a contraction of Statistics and Data. The former is used a great deal in business analytics and biostatistics, while the latter is popular in academic social sciences research, such as economics and epidemiology. SAS files are important because SAS is a software suite that performs advanced analytics, multivariate analysis, business intelligence, data management, predictive analytics, and is a standard for statisticians to do computational analysis. The most common SAS files have the extensions .stas7bdat and .sas7bcat, which are dataset files and catalog files respectively. You'll learn how to import the former as data frames using the function sas7bdat uppercase from the package sas7bdat lowercase. In this case, you can bind the variable file to a connection to the file urban_pop.sas7bdat in a context manager. Within this context, you can assign to a variable dfsas the result of applying the method toDataFrame to file. Stata files have extension DTA, and we can import them using pandas. We don't even need to initialize a context manager in this case. We merely pass the file name to the function readStata and assign it to a variable just like this. In the following exercises, you'll gain invaluable experience at importing these important file formats in Python as pandas data frames and then seeing what was inside them. Now it's your turn. Happy importing! According to the 2013 O'Reilly book, Python and HDF5 by Andrew Collette, in the Python world, consensus is rapidly converging on Hierarchical Data Format version 5, or HDF5, as the standard mechanism for storing large quantities of numerical data. Now, how large are we talking here? According to Collette, it's now relatively common to deal with datasets hundreds of gigabytes or even terabytes in size. HDF5 itself can scale up to exabytes. Let's explore with a concrete example from LIGO, the Laser Interferometer Gravitational Wave Observatory project. You first import the package h5py, and then import the file using h5py.file, remembering to use R in order to specify read-only. Printing the data type to the shell reveals that we are dealing with an h5py file. But what is the structure of this file? You can explore its hierarchical structure as you would that of a Python dictionary using the method keys. You see that there are 3 keys: meta, quality, and strain. Each of these is an HDF group. You can think of these groups as directories. The LIGO documentation tells us that meta contains metadata for the file, quality contains information about data quality, and strain contains strain data from the interferometer, the main measurement performed by LIGO, the data of interest. If you knew what data and metadata should be in each group, you could access it straightforwardly. However, if not, due to the hierarchical nature of the file structure, it is easy to explore. For example, let's say you wanted to find out what type of metadata there is. You could easily print out the keys. Now you know the keys, you can access any metadata of interest. If you're interested in description and detector, all you need to do is print out the corresponding values. You see that the data in the file is strain data time series from LIGO, and that the detector used was H1. Next, perhaps, you would like to check out the actual data. Great idea, and that's precisely what you're going to do in the upcoming exercises. Before you do so, it is also worth noting that the HDF project is actively managed by the HDF Group, based in Champaign, Illinois, and formerly part of the University of Illinois Urbana-Champaign. Now it's time for you to import and visualize some of the data that led to the validation of Einstein's theory of gravitational waves. Enjoy. MATLAB, which is short for Matrix Laboratory, is a numerical computing environment that is an industry standard in the disciplines of engineering and science. This is in part due to its powerful linear algebra and matrix capabilities, in part to its proprietary nature, and in part to how difficult the academic world finds it to shake off old habits. Regardless of the reasons for its widespread use, the fact of the matter is that a lot of people use MATLAB and save their data as .mat files, the file format native to MATLAB. Now, how can you import these into Python? Luckily for us Python aficionados, the standard library SciPy has functions loadmat and savemat, which allow us to read and write .mat files respectively. What exactly is in a .mat file, you may ask? To answer this, let's look at the MATLAB IDE. In particular, check out the MATLAB workspace, where all your variables are stored. This workspace can contain strings, floats, vectors, and arrays, among many other objects. A .mat file is simply a collection of such objects. Now this means when importing a .mat file in Python, we should expect to see a number of different variables and objects. In this code, I first import scipy.io and then load the file workspace.mat. Checking out what type of object results tells me that it's a dictionary. How this dictionary relates to a MATLAB workspace is straightforward. The keys of the Python dictionary are the MATLAB variable names, and the values of the Python dictionary are the objects that are assigned to the variables. In the above example, matx is a NumPy array corresponding to the MATLAB array x in your MATLAB workspace. It's that easy. Now it's your turn to import a MATLAB workspace and check out what it contains. Happy exploring!